Hello students, in this video lecture we are going to discuss about memory management. So before going into the various schemes of memory management, we have to understand the basic hardware that is involved in the memory management. There is a main memory, which is what we are referring as the RAM, and a set of registers. And there are machine instructions through which we can access the main memory. So whenever a program is executed, the current instruction being executed may need some data from the memory, and in that case it will provide an address, and that address will be used to fetch the value from the specific memory location or the memory address. But the during the execution of any program, the disk addresses never referred by any of the programs. The instructions always refer only the main memory addresses, never the disk addresses, and that is just because anything that needs to be executed has to be available in the main memory. Whether you are executing instructions or you are accessing data, they both have to be already fetched into the main memory, and only from the main memory CPU will execute them. So at no point of time CPU directly accesses the disk memory. In case if the data is not in the memory, then they have to be moved into the memory before the CPU can work on the data. So this is the basic arrangement. We have got that there is a main memory and some number of registers, and the disk is actually acting as a permanent storage but does not play any direct role in the execution of processes. It's only the main memory and the registers that are utilized by the CPU for execution. The difference between main memory and the registers is that registers are much faster than the main memory. So you can access the disk, you can access the registers in within a single cycle time. Cycle time uh, it's a kind of measure of the CPU's performance. So how many cycles it takes for a processor to complete an instruction can be used for the assessment of the CPU's performance. So normally register accesses are all completed in a single cycle time, but if it has to be accessed through from the memory, it involves the memory bus, because registers are part of the CPU. They are already inside the CPU, so in no time the data can be retrieved from the registers. But memory is a separate module. It's placed at a distance from the CPU. So if it has to access the memory content, then it has to send a request to the memory controller, and the data has to be fetched and then to be forwarded through the memory bus to the CPU. So this takes a lot of time, and so basically memory access will take many cycles, but register access will take a single cycle. And now we have to find some kind of a balancing between the speed disparity between the registers and the main memory. Registers are able to provide a much faster memory access or quicker access of content, but main memory takes much longer time. But we can't replace main memory by registers because there are only few registers available. So we need a little larger memory, which is kind of quicker comparing to registers, and larger like main memory. So the new memory has to be somewhat larger like the main memory and somewhat quicker like the registers, and that memory is what we are calling as a cache memory. So a cache memory is a faster memory and also reasonably larger memory, which is placed in between the registers and the main memory. So once a cache is made available, then execution will not directly go to the main memory, but it will take the content from the cache memory. So this reduces the time of accessing the content, whether it is instruction or data. Now what about protection? So protection in the sense, we have to protect the content of the user processes as well as the operating system from malicious programs, because the same main memory is going to is going to hold all the processes as well as operating system. If a program is written with a malicious intent, then it could manipulate the addresses of other processes, even the operating system. So it could result in corruption. The data processes could get corrupted. So that is a problem, and we have to protect the operating system and user processes from that kind of improper access manipulation. So we have a number of solutions for that, but the basic requirement is that the protection has to be facilitated by the hardware, because here the OS can't protect, because the OS itself needs to be protected. OS itself is a victim of lack of protection. So it has to be implemented at the hardware level, and so that with the help of the hardware we can differentiate the instructions as legal instructions and illegal instructions. So whenever an instruction requests for accessing a certain memory address, the OS should be able to determine whether that access is proper to the is a proper and it won't be affecting any other processes, or it is improper such that allowing it would corrupt some other process. So that has to be determined by some mechanism. That mechanism is something called as a base and limit registers. So there are these two registers are provided in every processor architecture, and the purpose of these two registers is that whenever a process is executed, its starting addresses will be loaded into the base register, and the size of the process is loaded into the limit register, and accessing the base and limit registers is a privileged instruction. That means that only the OS can access the base and limit registers to change the value or to read the value. No user process can access the base and limit registers, and so it remains protected. So it will not be modified by any process other than the operating system, because it requires a privileged instruction. And you know the process of running a privileged instruction, the process has to will be blocked, and the mode switch will happen from user mode to kernel mode, and the operating system will get into the CPU, then it will execute the privileged instruction, and then it will once again restore the state from kernel mode to user mode, and then the user process can resume its execution. So there is no direct manipulation of the base and limit registers by any of the user processes. So this is the solution that is provided for the protection. But how is it going to protect uh, the processes? We will see soon. For example, let us consider that the base register is loaded with the value of 300040, which is nothing but the starting address of a particular process, and the limit register contains 120900, which is nothing but the size in terms of bytes of that process. Now how do you interpret these two numbers is that whenever an instruction needs to be executed for that particular process, the OS will check whether the range of addresses falls within this number and this number. This is the range that is acceptable for that particular process. How this range has been assumed is that the starting address is directly given, the base address is given. This value is used to calculate the last address. So you can add these two numbers, you will come to know that this number is the last address in that range. So only instructions that refer to or try to access any address in that range will be permitted for execution. Any other address, for example address that is less than this or address that is greater than this, is easily detected to be out of range address, and the operating system will immediately trap the process. You know that that whenever the current process makes an illegal request, it will be trapped. So that process will be trapped. So every address generated by the processes will be compared with respect to their base and limit registers, and only if they fall within the proper range they will be executed, otherwise they will be stopped. So there is a, it will be trapped and treated as a fatal error. This is what that particular example. So we have a number of processes as well as the operating system. Now for this process there is a certain base and limit value. So accordingly every instruction pertaining to this process will be carefully evaluated whether it falls in this range. For example, if an instruction writes there is, if this process contains some instruction which modifies the value at a particular address, let us say that address is 420941, which means that it is trying to manipulate address of another process. So the OS should not allow it. How it will detect is that, as we have seen, the range are permitted for that process is only up to 420939, and since it is trying to attempt to, it is attempting to change an address in not in its range, this will be trapped. So this is a simple mechanism that is helpful in protecting the user processes among other processes as well as the operating system. This is the design we have made for this particular process. So whenever CPU generates an address as part of the current instruction, instead of directly going to the memory for with that address, it's first verified whether it is a valid address. So it's first compared with the base register whether it's in the starting address is not less than this, that it should be greater than or equal to the base address, and then it has to be less than the base and the sum of base and limit. That's how we have seen in the previous slide. Only if it means both the criterias, it will be further sent to the memory, otherwise it will be trapped. So in this arrangement, the operating system is have got the highest privilege that it can do anything in a computer. It can load the user processes. It has unrestricted access to any instruction. Privileged instructions can be executed only by the operating system in kernel mode, and whereas the user have got a very limited privilege that for any high privilege instruction he has to make a system call to the OS, and the OS will decide whether this can be facilitated or not. The next topic is called address binding. So you already got an introduction to this topic when you studied C++. So hope you remember that you studied something called a late binding. Late binding is with respect to runtime polymorphism. So whenever a function call is made, that function address has to be connected with the function call. See, there is a function calling statement somewhere in the main program, and the actual function is residing somewhere else in the memory, because a function is not part of the main function, it's loaded somewhere else. So before the function call is actually executed, the address of the function or the base address of the function has to be filled in the function calling statement. Only then at runtime it will work correctly, and this binding is typically done during compilation. But if it is delayed, up to the execution time, then it is called as a late binding. That is what you studied under the runtime polymorphism. So you can refer your material if you don't remember this particular concept. It's very important concept that everybody should remember and clearly know what is the meaning of runtime polymorphism. That is because that provides you the basis for this particular topic. So what is address binding? A program resides on a disk or in a as a binary file. Initially, before execution, program resides in the disk only. It's only when you make a call for execution, like the command for /a.out, the program gets loaded into the main memory. And now you know which model of the OS is responsible for that. It is the long-term scheduler, which loads the processes in executable or in exe format from disk into main memory. So it must be brought into main memory and placed within a process. And depending on the memory management, the process may be moved between disk and memory during execution. We have seen that swapping, there is a possibility called swapping. So even after a process has been successfully moved from disk into main memory, for some reason it may be moved back into the disk temporarily. So that particular process is called swapping, and swapping may also happen for any process. So the processes on the disk that are waiting to be brought into memory for execution form a queue. This is the queue of the long-term scheduler. The long-term scheduler has to make a selection out of the processes to be moved into the main memory. Normally the FIFO is good enough for making that selection. So as the process is executed, it accesses instructions and data from memory, and then finally the process terminates. So this is the cycle of a process execution. Initially it resides in the disk memory, and then when it has to be executed, it gets queued into a disk queue or the long term queue, and eventually it gets loaded into the main memory and becomes part of the ready queue, and then goes to the CPU, and depending upon its size, it may take multiple turns, then finally completed. And so this is how a program actually gets executed. Most systems allow a user process to reside in any part of the physical memory. That is, once the process is loaded into the main memory, it can be loaded anywhere in the main memory. It's not there is no particular address into which a process needs to be loaded. uh, but the problem with this approach is that during the program development, you won't have any clue where the program is going to be actually loaded at runtime. Initially, if you go back to the assembly language programming, the instructions were decided by the programmer. So while writing the instructions will have the address of the so for example, you have to write a go to statement. So go to a particular address. In that case, you would have hard coded the address directly. So the program execution will happen precisely based on the addresses that are provided in the instructions. But once we move to high level language programming, we have no control on the addresses, because address calculation happens at a later time. So this gives a challenge. We can't determine the addresses. So in most cases, a user program will go through several steps, like program development, where you are typing the coding, then you compile the program, then you execute the program, and then addresses may be represented in different ways during these steps. So we will know the actual addresses only at the third stage, when the program is under execution. But until that point of time, in all the previous steps, we won't know the precise addresses. So we can use some intermediate form to represent the addresses during the development and compilation. They are simply called as relative addresses. So relative addresses are logical addresses, or temporary addresses, which will be transformed into physical addresses during execution. And we can also call them as symbolic addresses. So a compiler will typically bind the symbolic addresses to relocatable addresses. Again, relocatable address is not the ultimate address. That should once again it has to go through a transformation to become physical address. So initially symbolic addresses are made use of in the programs, which are then converted into relocatable addresses. And then finally, the linkage editor or the loader will finally convert the relocatable addresses to absolute addresses or physical addresses. So these are the three stages of addresses as of now, but we will extend the list further later. But as of now, the program contains symbolic addresses. Compiler converts symbolic addresses to relocatable addresses, and then the loader converts the relocatable addresses to physical addresses or absolute addresses. This is what called as mapping. Now, type of address binding. We have seen a basic idea of binding. So address binding is about converting the symbolic addresses to absolute addresses. Now this binding can happen at different stages. That's what we call as types of address binding. So the binding of instruction and data to memory addresses can be done at any step along the way. The simplest time at which the binding can happen is during compilation. So when the program gets compiled, if the compiler is capable of binding the addresses, then it's called compile time binding. Initial programming languages like the Fortran, COBOL, they were able to do this because that was a simple system where one program gets loaded and executed. So the compiler knows that the address always starts from 0 and it goes to the maximum address depending upon the size of memory. So it was able to manage the binding on its own. So compile time binding, but we no longer have this kind of compiler binding in any of the modern programming languages. So what it will do is that it will simply copy the it will simply make the symbolic addresses by replacing them as a real addresses starting from 0. But the problem with this approach is that because the compiler binds the instructions to addresses, in case if the program gets loaded into a different region of addresses, then the entire program has to be recompiled. Otherwise it will go wrong. For example, the process has assumed that the program is going to be loaded starting from address 0. So wherever it finds addresses, it replaced them in the range of 0 up to the size of the process, so 0, 5, something like that. But unfortunately the program gets loaded not at our base starting address 0, address 50 for example. So what will happen is that the compile whatever the addresses that are filled by the compiler are no longer relevant because now the starting address has been changed into 50. So you have to recompile the program, only then it will become rectified and modified according to the new range of addresses. So this is the drawback in the compile time binding. Compile time binding is a simple mechanism and it works only if the loading process is never going to change the addresses where a process is going to be loaded. But if it is likely to change, then compile time binding will fail, or you have to recompile the process multiple times. The next better timing of loading is address binding is load time binding. So loader means that after the program has been compiled successfully and its exe is generated, in order to execute it, it has to be loaded into the main memory, somewhere into the main memory. That particular module is what we are calling as a loader, or in other terminology we can also refer it as long term scheduler. So a long term scheduler is nothing but the loader. So during load time, this can be done better because now it is finalized where the process has to be loaded into the memory. Depending upon the availability of memory space, a particular memory can be chosen by the operating system, and the loader knows clearly what is the starting address of the process in the memory. So at load time, this can be taken care. The address binding can be dealt with during load time instead of at compile time. So the compiler will just fill the addresses by some relocatable code. It won't be an actual address, but it's a temporary address called relocatable address. So the actual binding will be delayed until load time. Compiler binds name to relative addresses. So loader then converts the relative addresses to physical addresses. So that is what happens under the load time binding. and no relocation allowed during, and okay, so this particular method of binding is better than compile time binding, because if you fix the if you do the binding at the time of compilation, then you have to recompile the program multiple times. Whenever the program has to be loaded into different addresses, you have to accordingly recompile the program. But in this case, load time binding, you don't need to recompile the program, because it's only the loader that is going to convert the relative address into actual address, not the compiler. So compiler's job is already over, and you don't need to recompile the program again. So load time compiling address binding is better than the compile time binding, but it is still not good enough. It is better but not sufficient, because relocation is not permitted during execution. So what do they mean by relocation is that, carefully listen to this scenario. A process has been loaded into main memory, which means that its addresses are fixed. Once the process is loaded into main memory, its addresses are already fixed. But during execution of the process, imagine that the operating system decides to swap the process. That means that it is going to be moved out of main memory into the disk memory. This may happen because of reasons of memory shortage. So let's say a high privileged process has to be immediately loaded into memory, and there is no sufficient space. So the OS may now choose to replace this particular low priority process to bring the high priority process. After some point of time, the one that was swapped to the disk has to be brought back into the main memory. But this time, that particular memory address that was previously allocated to that process may not be currently available. It's like you stayed in a particular room in your hostel, and you vacated this room for when during the summer holidays, and when you come back again after the holidays, you find your room occupied by some other person. So you simply have to go to a different room. But here it is going to be a difficult process, because the loader has converted all the instructions pertaining to the previous range of addresses, but now you are going to load it into a different address range, but that is not allowed under load time binding. So no relocation is provided or possible under load time binding. As a result, you can't do swapping. So swapping is impossible with the load time binding. So we have to move on to a better binding technique, which is called as the execution time binding or dynamic binding. So this is the ultimate binding technique. Here what happens is that the binding is delayed till execution. So even during loading, the addresses are only kept in the relative form. They are not converted into physical addresses. So even the CPU generates only relative addresses. Only at the time of execution, the addresses are converted to physical addresses. So it is the responsibility of the memory management unit to bind the relative addresses to physical addresses. Everywhere the addresses are only seen as relative or logical addresses. Only at the level of the memory management unit, the actual address is calculated or transformed. So it requires a special hardware to convert the relative address to physical address. That special hardware is what I am referring as MMU or memory management unit. So these are the three binding techniques. So address binding can be done either at compilation or at loading time or at execution time, and we have seen the merits and demerits of each one. And now, because of this arrangement that you are going to have the addresses are going to be differing between the physical address and the relative address or logical address. And one more thing that needs to be included in this discussion is virtual memory. We have already seen that besides the physical memory or the main memory, we are also going to utilize a portion of the secondary memory as a virtual memory. So the logical memory is the collection of virtual memory and the main memory, whereas physical memory is only the main memory. So we have to differentiate the memory as a logical memory and physical memory. When you say logical memory, it is a larger memory than the actual main memory. It's larger because we have included the secondary memory, a portion of the secondary memory also as part of the main memory. So it has been enlarged, but actual memory is only smaller, which is the physical address. So we are going to treat them as two separate address spaces, logical address space and physical address space. So whenever an address is generated by the CPU, it's only called as a logical address because that address is pertaining to the logical address, that is main memory along with the physical virtual memory. But eventually, for execution, this logical address has to be mapped to a physical address, and that will be done by uh, the memory management unit. We will see it. So that MAR is commonly referred to as a physical address. The compile time and load time address binding methods generate identical and physical and logical addresses, but it is in the runtime or execution time binding there is going to be a difference between logical and physical address. So today every computer is basically employing execution time binding. We don't need to bother about compile time and load time binding in present computers. It's all dynamic binding. So under dynamic binding, whenever you see an address, you are basically talking about logical address. For example, think of your C program where you made use of pointers. So by declaring a pointer, you can store the address of a variable into the pointer variable. You can even display that address. So now with the idea of logical address, my question is that when you print the address of a pointer, whether you are printing the physical address or the logical address. The difference is that if you say physical address, that means it is the actual address of the memory location. When you say logical address, it's a relative address which will be somehow converted into physical address uh, by the memory. So the answer is that it is actually the logical address, not physical address. So only the MMU is aware of the physical address. So whenever an address is generated by the CPU and it is sent to the memory management unit, the memory management unit will have the method to convert that logical address into physical address and then fetch the data from that address. But for everybody else, it is not going to be known. The physical address is not known to neither to the operating system or to the CPU or to the user program. It's only known at the level of the memory management unit. We will discuss this the implementation of this particular scheme in under paging. So by the time it will become much clear, but as of now you just have to grasp the point that whenever an address is generated and sent to the memory for fetching, it's in the form of logical address, and the memory management unit will have that the methodology or the scheme for converting that logical address into physical address, and then it will fetch the data from that address. We can also refer to the logical address as virtual address because it involves the virtual memory. We can refer to an address generated uh, at the CPU level is as a virtual address, and we call it as a logical address space and physical address space. So logical address space is collection of uh, the physical addresses and the virtual addresses, whereas physical address space is purely the addresses pertaining to the actual main memory. So and as I have been repeating, it is the role of the responsibility of the memory management unit to convert the virtual address into physical addresses. So it is the only one that has the intelligence to convert the virtual address into its equivalent physical address. We will see how this mapping is actually done under paging. Uh, let's take a simple example here. Assume that the size of the operating system is 50 bytes. Let us assume that the OS is occupying 50 bytes, and there are different processes needing this much of memories. So process 1 needs 5 bytes, process 2 needs 10 bytes, and so on. Now, how much of main memory is minimum required to load and execute all these processes, including the OS, which is nothing but the sum of these processes and the operating system, which is in fact 89 bytes. So 89 bytes are minimum required to load all of them into the main memory, because you have to load each one as per its requirement. So 50 bytes are needed to load the OS, and then these respective addresses are needed for each process. So totally it will take 89 bytes. But if you introduce the virtual memory into the system, then the total memory won't be 89 bytes, because you know very well that whenever you employ virtual memory or the secondary memory in the form of a virtual memory, you have the option to load some of the part of the process into main memory and the remaining part into the secondary memory or virtual memory. So you don't actually need 89 bytes. It will be much lower than 89 bytes. It can be even half of the 89 bytes that is going to be required. So this is how you are going to now load processes. You will utilize the disk to load uh, some portion of the processes. So what is currently needed alone is loaded into main memory. So the OS is only loaded for 30 bytes. The remaining 20 bytes are loaded into the virtual memory, and similarly all other processes are also partially loaded into main memory and partially loaded into the disk memory. And during execution, if suddenly this part of the process is required for execution, then it will be dynamically loaded into the main memory. Not until then. So this is what we are now referring as a logical address space and physical address space. The physical address space is only the main memory. Logical address space, the collection of main memory and the disk memory. So the complete memory space is called as logical, whereas only the main memory is called as physical. Address mapping. Next relative topic is address mapping. Logical address space is larger than the physical address space. So before going to this topic, let me recall a similar mapping you studied in the previous semester of cache mapping. So what was the idea behind cache mapping? You have main memory and a cache memory. Main memory is much larger than the cache memory. So you are going to load a portion of the main memory into the cache memory, and as a result of this you have to somehow map the content of main memory with respect to the cache memory. So let's say you have loaded a process in a portion of a process into the cache memory. Now when CPU says that I want this process to be executed, it only says the address of the main memory, not the address of the cache memory. CPU does not recognize the cache memory, and it never refers to the address of the cache memory. It always points out the address of the main memory. So it sends the address of the main memory. Now it has to be found out where this particular process could be residing in the cache memory. For that you need a mapping. We studied that as a cache mapping. The same way, here we have got an arrangement that you have a main memory and you have a disk memory. So some content of the processes are loaded into the disk memory. So whenever an instruction address is provided by the OS, you have to know where it can be found, whether it can be found in the main memory or it has to be retrieved from the disk memory. That is what the idea of address mapping here. So CPU addresses memory only in terms of its logical address space. It does not deal with the physical address. So CPU creates the illusion of a much larger main memory by collectively treating the secondary memory and main memory as a single large entity, and so it will always give addresses pertaining to the logical address space. As a result, the number of logical addresses will be, or virtual addresses will be, much more than the physical address. See, you can understand this very simply. Logical address is always larger than physical address, because physical address means only the RAM memory, but logical address means RAM plus disk. So it's going to be larger. For example, the logical address space could be 128 bytes, which requires 7 bits. Whereas the physical address could be much lower, smaller than that, which is only 64 bytes, needing only 6 bits. This is just an example. So similarly, there will be a difference in the logical address space and the physical address space. We will discuss about the proper mapping technique under paging, but as of now we will just learn a simple technique to do the mapping with the help of base register. So it's only for the time being we are going to make use of the base and limit register for this purpose, but later we will discuss a more sophisticated mapping mechanism. So how do we do it with the base register? uh, you can call it, I mean, now we are going to refer the base register as a relocation register, because it's going to help in converting a logical address to physical address. We just rename it as a relocation register, point number 1. But the content is not going to be different. It's going to hold the starting address of any process. Now what happens is that the value in the relocation register is added to every address generated by a user process at the time of address is sent to the memory. For example, see, I just want to let you know a similar example you studied earlier. You all have declared arrays in C and C++. This is how the declaration was done. Int array size 10. After this declaration, you know what is the meaning of array of 5. The meaning of array of 5 is that fifth address from the base address. Okay, from the compiler's point of view, array of 5 is nothing but fifth address from the base address. So that is exactly what we are referring here. So once you have the base register, the actual address generated by the process can be simply added with the base register to know the precise address. That is logical address to physical address. What do you think will happen here? Whether it will be, I'm actually trying to, it should have been array of 5, but not by mistake, but intentionally I have written it as 5 of array. So it won't actually result in any error, because I said array of 5 means base address plus 5. 5 of array means 5 plus base address, so it won't make any difference. The result will still be same. So both this will also work in C. So this is an example from the OS. If the base address is at 14,000, if the base is at 14,000, then an attempt by the user to address location 0 is dynamically relocated to 14,000. They are just added, and an access to location 346 is mapped to 14,000 plus 346. So basically every address generated for the process will be added with the base address to get the actual address. This is how it's being done. So there is a relocation register through which you convert the logical addresses into physical addresses before accessing the main memory, and the one that is doing this process is called as a memory management unit. So we have seen a very simple rudimentary technique by which the logical address can be converted into physical address, but the actual operating systems employ much more sophisticated mechanism for this translation, which we will be discussing later. So this is the idea of the introduction to the memory management. Next we will explore more more complex and more sophisticated memory management schemes like paging and segmentation. Thank you.